In single-phase systems, the phase-to-neutral fault current can indeed be higher than the three-phase fault current, especially in very short feeders. This phenomenon primarily occurs when the fault current is significantly limited by the transformer's impedance. The calculation program accurately accounts for this condition if the transformer is sufficiently large. However, if the transformer is too small, the program may not accurately reflect the higher fault currents that can occur, leading to incorrect results. To determine if this condition applies, examine the transformer's X/R ratio, that is, the ratio of its reactance to its resistance. If the X/R ratio is less than 1.2, this suggests that the transformer is too small to accurately calculate the single-phase fault current in this scenario. Consequently, the fault current results produced by the program under these conditions may be incorrect. Conversely, if the transformer's X/R ratio is greater than 1.2, it indicates that the transformer is adequately sized, and the fault current results from the program should be reliable. If the transformer is found to be too small based on its X/R ratio, the recommended solution is to input data for a larger transformer into the calculation program. This will provide a more accurate assessment of the potential fault current. The reason for the higher phase-to-neutral fault current in short feeders stems from the fact that the impedance limiting the fault current is primarily the transformer's impedance. In a three-phase fault, the fault current path involves the impedance of all three phases of the transformer. However, in a phase-to-neutral fault, the current path includes only one phase winding and the neutral conductor. The neutral conductor typically has a lower impedance than the phase windings. This lower impedance path results in a higher fault current. Additionally, the single-phase fault current calculation considers the impedance of the entire single-phase circuit, including the service conductors, the transformer, and the feeder conductors. The shorter the feeder conductors, the less impedance they contribute to the overall circuit impedance, resulting in a higher fault current. The transformer X/R ratio is crucial because it reflects the relative influence of reactance and resistance in the transformer's impedance. Reactance is a frequency-dependent opposition to current flow caused by inductance and capacitance. Resistance is the opposition to current flow that dissipates energy in the form of heat. A low X/R ratio indicates that the transformer's resistance is relatively high compared to its reactance. This higher resistance limits the fault current, preventing it from reaching the levels that would be seen with a larger transformer having a lower resistance. The program calculates the available short-circuit current at the end of the feeders. The available fault current is the maximum current that a circuit can deliver under short-circuit conditions. It is a critical parameter for selecting appropriate overcurrent protection devices such as circuit breakers and fuses, and for ensuring the safety of electrical systems. The available fault current is determined by the source voltage and the impedance of the circuit up to the point of the fault. The higher the source voltage and the lower the impedance, the higher the available fault current. In single-phase systems, the phase-to-neutral voltage is typically lower than the phase-to-phase voltage. However, the impedance of the neutral conductor is also typically lower than the impedance of the phase conductors. This combination of factors can result in a higher phase-to-neutral fault current than a phase-to-phase fault current, especially in short feeders where the impedance of the feeder conductors is minimal. When selecting overcurrent protection devices, it is essential to ensure that they have a short-circuit interrupting rating that is greater than or equal to the available fault current at their location. If the interrupting rating of the overcurrent protection device is less than the available fault current, the device may fail to interrupt the fault current safely, leading to equipment damage, fire, or personal injury. The calculation of fault current involves several steps. Firstly, determine the transformer's impedance. Transformer impedance is typically expressed as a percentage of the transformer's kilovolt-ampere rating. This percentage represents the voltage drop across the transformer at its rated kilovolt-ampere output. Secondly, calculate the impedance of the feeder conductors. The impedance of the feeder conductors depends on their length, size, and material. The impedance is typically expressed in ohms per foot. Thirdly, calculate the total impedance of the circuit. The total impedance is the sum of the transformer's impedance and the feeder conductor's impedance. Fourthly, calculate the available fault current. The available fault current is calculated by dividing the source voltage by the total impedance. It is important to note that the calculated fault current is the maximum potential fault current. The actual fault current may be lower due to factors such as arc impedance and the presence of other loads on the circuit. The program simplifies these calculations and provides a more accurate assessment of the available fault current by taking into account various factors such as the transformer's X/R ratio and the length and size of the feeder conductors. Using a larger transformer in the program is a practical approach when the X/R ratio is less than 1.2 because it effectively simulates a system with a lower impedance, which is more representative of the actual conditions in a short feeder with a high potential for phase to neutral fault current. It's also important to understand the limitations of any fault current calculation tool. While the program can provide valuable insights, it is not a substitute for sound engineering judgment and a thorough understanding of electrical systems. Always verify the results with other methods and consider the potential for unforeseen factors that may affect the actual fault current. Furthermore, it's crucial to regularly update the program and its data to reflect any changes in the electrical system, such as upgrades to the transformer or modifications to the feeder conductors. Accurate and up-to-date information is essential for reliable fault current calculations. Remember that electrical safety is paramount. Always consult with a qualified electrician or electrical engineer when working on or designing electrical systems. Fault current calculations are a complex topic, and it is essential to have the expertise and knowledge to perform them accurately and safely. The National Electrical Code, or NEC, provides guidance on fault current calculations and overcurrent protection. Refer to the NEC for specific requirements and recommendations. For example, NEC Section 110.9 addresses interrupting rating and requires that equipment intended to interrupt current at fault levels be rated for the available fault current at the line terminals of the equipment. NEC Section 110.10 addresses circuit impedance, short circuit current ratings, and other characteristics. This section requires that the overcurrent protective devices, the total impedance, component short circuit current ratings, and other characteristics of the circuit to be protected shall be selected and coordinated to permit the circuit protective devices to clear fault to limit the damage to electrical equipment. NEC Section 250.2 addresses grounding of electrical systems. Proper grounding is essential for providing a low impedance path for fault current to return to the source, which helps to ensure that overcurrent protection devices operate quickly and effectively. NEC Section 310.15 addresses ampacity of conductors. The ampacity of a conductor is the maximum current that it can carry continuously under specified conditions of use without exceeding its temperature rating. It is essential to select conductors with an ampacity that is sufficient for the load they will carry and for the available fault current. NEC Section 430 addresses motors, motor circuits, and controllers. Motors can contribute significantly to fault current, so it is essential to consider their contribution when calculating fault current. In addition to the NEC, other industry standards and guidelines provide valuable information on fault current calculations and overcurrent protection. These standards and guidelines can help to ensure that electrical systems are designed and installed safely and in accordance with best practices. By understanding the principles of fault current calculation and overcurrent protection, and by following the requirements of the NEC and other industry standards, it is possible to design and install electrical systems that are safe, reliable, and efficient. The X/R ratio of a transformer is an important parameter that affects the magnitude and duration of fault currents. A low X/R ratio indicates that the transformer has a relatively high resistance, which limits the magnitude of the fault current. A high X/R ratio indicates that the transformer has a relatively low resistance, which allows for a higher magnitude fault current. The duration of the fault current is also affected by the X/R ratio. A lower X/R ratio causes the fault current to decay more quickly, while a high X/R ratio causes the fault current to persist for a longer time. The duration of the fault current is important because it affects the amount of energy that is dissipated in the fault. The more energy that is dissipated, the greater the potential for damage to electrical equipment. The X/R ratio is typically provided by the transformer manufacturer. If the X/R ratio is not available, it can be estimated based on the transformer's kilovolt-ampere rating and impedance. In general, larger transformers have lower X/R ratios than smaller transformers. The X/R ratio is used in fault current calculations to determine the appropriate settings for overcurrent protection devices. Overcurrent protection devices are designed to interrupt fault currents quickly and safely. The settings of these devices must be coordinated to ensure that they operate properly and that they do not cause nuisance tripping. Nuisance tripping occurs when an overcurrent protection device trips unnecessarily, interrupting power to a circuit. Nuisance tripping can be caused by a variety of factors, including incorrect settings, harmonics, and voltage fluctuations. To avoid nuisance tripping, it is important to carefully coordinate the settings of overcurrent protection devices. The X/R ratio is an important factor to consider when coordinating these settings. The X/R ratio is also used in power system studies to analyze the behavior of electrical systems under fault conditions. Power system studies are used to identify potential problems and to develop solutions to improve the reliability and stability of electrical systems. In addition to the X/R ratio, other factors that affect the magnitude and duration of fault currents include the source impedance, the conductor impedance, and the type of fault. The source impedance is the impedance of the power source that is supplying the fault current. The conductor impedance is the impedance of the conductors that are carrying the fault current. The type of fault can be a short circuit to ground fault or an arc fault. A short circuit is a low impedance connection between two or more conductors. A ground fault is a low impedance connection between a conductor and ground. An arc fault is a fault that involves an electric arc. Arc faults are particularly dangerous because they can generate high temperatures and can cause fires. To protect against arc faults, arc fault circuit interrupters, or SIs, are used. SIs are circuit breakers that are designed to detect and interrupt arc faults. SIs are required in many residential circuits by the NEC. Fault current calculations are an essential part of electrical system design and safety. By understanding the principles of fault current calculation and overcurrent protection, it is possible to design and install electrical systems that are safe, reliable, and efficient. Remember to consult with a qualified electrician or electrical engineer when working on or designing electrical systems. Their expertise is crucial for ensuring safety and compliance with electrical codes and standards.